So you learned this recently. If you were to plug a 4 into the numerator here, you would get 4 minus 0, which is 0. When you plug 4 into the denominator, we get 16 minus 12 minus 4. So that's 16 minus 16, which is also 0. So we get an indeterminate form. So that doesn't help us find the limit. What we need to do is first factor out a negative in the numerator. Make sure you rewrite the limit notation in front of each step. When you factor a negative out, you're allowed to flip the order of the terms in that binomial. Let's factor the denominator. Then we can cancel. And that offending term, x minus 4, that gives us the 0 is now gone. So we can go ahead and plug in here, and we're going to get negative 1 over 5. So let's talk about what's happening on this graph. So do you see how there was a term that canceled out? That means the graph has a hole. Where is the hole on the graph? Well, the hole is at the coordinates 4. And then we plug 4 into the remaining expression, and that's where we get the negative 1/5. So this graph looks like the function negative 1 over x plus 1, which is related to the graph of 1 over x, except it was shifted 1 unit to the left, and it kind of flips to the opposite quadrants. So our graph kind of looks like this. Here and here. But what's happening when we get over here to 4 is the graph has a hole in it at 4 and then negative 1/5. So even though there's a hole in the graph, the limit still exists. So there was a problem when we initially plugged in 4 to the function. It gave us 0 over 0. It was because that function is undefined at 4 because of the hole there. We just had to factor and cancel, and then we could plug in and find out what value the function was approaching as x approached 4. And so this limit does exist because there's just a hole in the graph, and a limit can exist if there's just a hole in the graph. Okay, moving on. Okay, these graphs have vertical asymptotes. The reason I can tell from the function that there's a vertical asymptote is this is the offending factor. We can't cancel that out by doing any algebra. We can't cancel these x's out because they're both added or subtracted to something. When you have a rational expression and you have a factor in the denominator that you cannot cancel out, and that factor has a 0, the graph is going to have a vertical asymptote. So what happens at a vertical asymptote? Well, there's 3 options. At a vertical asymptote, you could have both sides approaching positive infinity, and in that case, the limit would exist and it would equal infinity. You could have one side approaching negative infinity, one side approaching positive infinity, and in that case, the limit simply would not exist. And then in the third case, you could have the limits approaching negative infinity on both sides. So we know that there is a vertical asymptote at x equals 3. What we need to do is we need to find the limit as x approaches 3 from the left of this expression and see if it goes to negative or positive infinity. And then we need to find the limit as x approaches 3 from the right of this expression, and again, see if our limit goes to positive or negative infinity. So what we're going to do is we're going to consider a number a little bit less than 3, like 2.999, because we're approaching from the left. If I were to plug 2.999 into the numerator, I'm going to get a big number. I'm going to put approximately here. So I'm going to add 2.999 to 7. So I'm going to get 9.999. That's bigger than what I get on the bottom if I subtract these. If I put a 2.99 in for x and subtract 3, I'm going to get negative 0.0001, I believe. Maybe that's too many zeros. So when you take a big number or a normal size number and divide it by a small number, you get a big answer. So this answer is going to approach infinity. So our left-hand limit is going to equal infinity, but negative because we're doing a positive divided by a negative. Let's go ahead and do our right-hand limit. So let's consider an x a little bit bigger than 3, 3.001. So when we add that to the numerator, I'm going to get 3.001 plus 7, which is 10.001. And I'm just approximating, that's why I put the squiggly lines there. I'm just seeing what's happening. And then in the denominator, I plug in and I get 0.001 when I subtract. Well, when I divide, actually I'm going to go ahead and divide that just to see how big that number is. And I probably could do that without a calculator just by moving the decimal place over. I get 10,001. So that becomes a very big number, and so this is going to approach positive infinity. So since my left-hand limit is negative infinity and my right-hand limit is positive infinity, this is going to be DNE. The limit does not exist. So for the second example, I'm sorry if you already wrote it down. I changed it slightly. I paused the recording and changed it slightly. So this is the example we're going to look at. So on this example, we're going to, again, notice that there's a vertical asymptote on the graph at x equals 3. Because this offending factor, x minus 3 on the bottom, I can't do any algebra to cancel it out. So again, I'm going to consider the left-hand limit as x approaches 3. And the right-hand limit as x approaches 3. Okay, so at a vertical asymptote, the limit's either going to approach positive or negative infinity, and so we just have to check the signs. So again, we're going to consider what happens when we plug in a number close to 3 on the left-hand side, like 2.999. So imagine plugging 2.99 into the numerator. We'd get a positive. 2.99 plus 7 is positive. So now instead of working with actual numbers, we're just going to work with the signs. If we plug 2.999 into the denominator and subtract 3, we get a negative, but then when we square it, we get a positive. It's going to be a teeny tiny number. That's why when I divide, I end up with a huge number. Whenever you divide by a very small number, the output gets really, really big. But look, we have positive divided by positive, so this limit is going to equal positive infinity. So on the left-hand side of this vertical asymptote, the graph would go to positive infinity. Okay, this one, we're going to plug in 3.001. And if we plug that into the numerator, we get a positive. Plugging it into the denominator, we get, again, a positive because we're squaring. So we do a positive divided by a positive. Our right-hand limit is positive infinity. And this limit does exist. This limit is going to equal positive infinity since both sides of the vertical asymptote, the graph approaches positive infinity. Okay, this next guy is a very important function. So on this graph, we're going to talk about what the graph looks like. So here's one way that we can think about this graph. Let's just go ahead and plug in some x values. Like let's plug in 0. Well, it'd be undefined at 0 because we'd have a 0 in the denominator. Let's plug in some negative values. Plugging in negative 1, we're going to get positive 1 over negative 1, which is negative 1. Plugging into the function negative 2, we get positive 2 over negative 2, which is negative 1. Plugging in negative 3, we get positive 3 over negative 3, which again is negative 1. Any negative value, even decimals, plugging in negative 0.01, we'd get a positive 0.01 divided by a negative 0.01, so we'd get a negative 1. So what output do we get anytime we plug in a positive? Well, we would get positive 1. Plug in 7, you'd get 7 over 7, which is 1. Plug in 2, we get 2 over 2, which is 1. So this very important function has a graph that looks like this. So this limit does not exist. Why? Our left-hand limit as x approaches 0 is negative 1. If we want to write that down, we can. We can tell from the graph as x approaches 0 from the left, our limit equals negative 1. And we can tell from the graph as our limit approaches 0 from the right, our limit equals positive 1. One more very important thing about this function is that it can be written as a piecewise function. So this guy is equal to the piecewise function. The function equals -1 when x is less than 0, and the function is equal to 1 when x is greater than 0. Okay, what about the function on the bottom? Well, we replaced x here with x minus 4. So if you replace an x with an x minus 4 in a function, it shifts the function 4 units to the right. So what's happening for this bottom function is it's the same graph that we had above, where we have these horizontal lines with an output of 1 and -1, except the whole thing was shifted 4 units to the right. So this is what our graph looks like. So if you're finding the left-hand limit of this function as x approaches 4, it's going to equal -1.